Welcome back to yet another video on our channel Euclid Mathematics. We have started lecture series on ring theory, complex analysis, real analysis, linear algebra, calculus of variation, and other subject too. So within that, we have started the lecture series on ring theory. Already I uploaded plenty of the videos on ring theory. So without further ado, let's get start our today's lecture, which is completely based on the ideal from ring theory. I will explain to you all the definition of ideal and then we'll go for some of the examples from ideal. So now let's get start. So here in our question, the definition of ideal, it says that if we have two elements in our ring, that ideal, which is I non-empty subset of R, then there is a two elements which exist in I, their subtraction it goes to I, and if one element from ideal and another element from ring, their multiplication it goes to the ideal. Okay, then we say that our ring is having ideal. Generally ideals are having two types, one is a left ideal and another is a right ideal. Okay, so let's start the definition of a left ideal. Here the definition of a left ideal, it says that let I is a non-empty subset. So we need I is a non-empty here of our ring R. Then I under addition dot is an ideal of R. Okay, is an ideal of R if first option is given. Okay, so our first condition, it says that if every element from our ideal and there exists, we have another all elements, okay, from the ideal being all A belongs to I, all B belongs to I, their subtraction it goes to ideal. Okay, and second condition, if all A belongs to I, all R belongs to it is a ring here. Okay, R we have to take from ring, A from ideal, then R into A, which is need to go there in ideal. Okay, then we say that it is a left ideal. For right ideal, we have same condition. Okay, but only the second condition here, R into A into R belongs to I. Okay, all A belongs to I, R belongs to I, A into R belongs to I. Okay, so left ideal means R is this side here and right ideal is R this side here. Okay, this is only difference between left ideal and right ideal. If any ring which has a left ideal and right ideal, then we say that our ring is having ideals. Okay, so these are the only definition from ideal. Okay, so these are quite easy definition, but let's get started. Some example here that can be helpful to understand the definition of ideal. Okay, so I consider here M2R, it is a 2 by 2 matrix. Okay, so that 2 by 2 matrix is having element AB00 and AB from the ring. It's a right ideal of M2R. Okay, so we have to prove that whether it is the right ideal of M2R or not. So if we have to prove it is a right ideal, then we have to satisfy this first and second two condition. First, A belongs to I, B belongs to I, A minus B belongs to I, and second, A belongs to I, R belongs to I, A into R belongs to I. Okay, so prove first a condition. Okay, so when if we wanted to show that S is a right ideal of M to R, then take the two element from S. Okay, so in general you may take any element that we have to represent this element from our set. Okay, so I consider A as A1, B1. So AB it is from the R. So I consider A as A1, B1, remaining two element 0, 0 as it is from our set S. Okay. And again, B element here, A2, B2 and 0, 0 from set S. Okay. So I got the two element here. So A and B. Now I have to prove here that A and B possesses a right ideal property. Okay. So take the subtraction. So our first property, it says that A belongs to ideal, B belongs to ideal, then their subtraction need to go there in ideal. Okay, now we may go through their corresponding element subtraction. So A1 minus A2 here, B1 minus B2 here. Okay, 0, 0 here. Their subtraction A minus B is A1 minus A2, B1 minus B2, 0, 0, which goes to the set yes. Okay, so this is our first condition, it hold for a right ideal. Now we have to go for the next condition, which is A belongs to I, and take another element which is R belongs to ring, and prove that A into R belongs to I. Okay, we have to take it from the ring. Okay, so A, which is from our set yes, which is A1 B1 0 0. Okay, which is from the our ideal. Okay, yes is ideal considered here, so we have to prove whether it is ideal or not. Okay, and M2R means you may take any element which is a 2 by 2, which is a non-zero 0, anything there. Okay, just we have to take such a counter example that can violate our definition only. Okay, so I consider here A1 B1 0 0, which is from the ideal from our yes set yes, which is ideal here, and R I taken from ring M2R. You may take any element, so I consider here A B C D here from M2R. So prove that A into R, which is also the element of ideal. Okay, so A into R is A1 B1 0 0, A B C D. Okay, so multiply these two elements, so we will get the this row into this column this element, this row into this column this element, this one into this again this. Okay, so we can see here. So first element is non-zero, second element is non-zero, and third, fourth element is zero, which is a similar format of our ideal yes. Okay, so this set represents the ideal yes. Okay, so if it is hold here, then we say that our yes is a right ideal of M to R. Okay, so this is the right ideal for M to R. That one we have to show here only. Okay, so I hope you all have understood this example. So let's get start one more example. So here in my second example, I changed their places A0, B0. I taken yes as another ideal A0, B0, and we have to prove that AB from R, which is the left ideal of M to R. Okay, previously we proved there as a right ideal. Now we have to go for left ideal. Okay. Now here take the element from set yes. A I consider here, B I consider here, which can represent our set A. Yes. Okay. So A0, B0, okay, A1, B1, 0, 0, A2, B2, 0, 0, okay. So you may take this one, or okay, you may take this one A1, AB, 0, 0. That means just I alter here the row into column and column into row. Okay, if we change the rows to column, columns to row, that matrix doesn't affect. Okay, so here A1, B1, 0, 0, A2, B2, 0, 0. These are the elements from our set yes. Okay, so I converted just row into column, column into row. And I proved it here A minus B, which is from our ideal yes, and A into R, anything you may select. Okay, as we considered in previous example, A1, B1, A, B, C, D, which is from our M to R. Okay, and prove it here that their multiplication A1, A, B1, C, A1, C, B1, which is not goes to our set. Okay, which R into I, which not goes to our set ideal yes. Okay, set means ideal yes. So yes is not left ideal of M to R. A into R into A, it is never hold in our matrix multiplication. Okay, you need to remember this one. So sometimes if a left ideal hold for our ring, then we cannot say that right ideal hold too, because matrix multiplication it is not commutative. So that's why we cannot say about this. So that's why R into A R it is not equal. So it is a left ideal. Sorry, it is a right ideal but not left ideal. Okay. So this property highlight here. So this example do not satisfy the property of a left ideal. Okay. So which is the property I wanted to explain here. If R is a commutative ring like A into B, B into A, then every left ideal of ring is a right ideal of ring. Okay, that we earlier proved in our previous example. Okay, so in my second example here we can see I is equal to integer I taken Z is an ideal of Q. So we have to prove that whether it is ideal or not. Okay, so ideal work like in group theory we learn normal subgroup. Okay, so normal subgroup work as a factor group R by Q, which is the factor group. So normal subgroup work there as a in a group theory normal subgroup like a ideal. Okay, and in a ring theory it is a similar like ideal. Okay, so these are the relation between these concepts. Okay, so if you wanted to understand ideal properly, we need to know normal subgroup these conditions very well. Okay, so if you wanted to see this condition, you may check it into my playlist. Okay, so here in my second example, I have to prove that Z is an ideal of Q. Okay, so if Z ideal of Q or not, we have to check it here. Okay, so take some counter example that can define our set is ideal or not. Okay, so I consider 2 from Z and 1 by 3 from Q, but 2 multiplied by 1 by 3, it is not goes to Z. Okay, so 2 into 1 by 3, it is a fractional part, it is not belongs to integer part. So we say it here that property highlight our examples. Okay, so main property of our definition. Okay, so I which is equal to Z is not ideal of Q. Okay, because 2 into 1 by 3 does not belongs to Z, so Z is not ideal of Q. Okay, so if Z is not ideal of Q means Q belongs to R belongs to complex belongs to quotient integer. So Z is not ideal of a real number, complex and quotient integer. Okay, similarly Q. Okay, you have to try for Q. So this one is only for our today's lecture. I hope you all have understood the definition of ideal along with some of the example. So thank you everyone. Thank you for my today's lecture.